All right, so it's our great pleasure to introduce Robert Wille for this exciting keynote on design, automation, and software tools for quantum computing. Robert is a full professor at Technical University of Munich, and he also has a position as a chief scientific officer at Software Computer Center Hagenberg in Austria. And he received his diploma and doctoral engineering degrees in computer science from the University of Bremen in Germany in 2006 and 2009 respectively. And then he has been working there for many years. And then he started until 2022, he was a full professor at Johannes Kepler University in Linz in Austria. Then he moved recently to Munich. His research interests are in the design of circuits and systems for both conventional and emerging technologies. He has published more than 350 papers and served in editorial boards as well as program committees for several journals and conferences such as TCAD, ASP, DAC, DIT, and ICCAD. And recently he was also awarded very prestigious ERC Consolidator grant on the topic of this talk, I think, as well. And he also have won several Best Paper Awards and also Under 40 Innovation Award, Google Research Award, and many more. So with this, I would pass to Robert for the keynote. Robert, please go ahead.
Thank you. Thank you very much for the kind introduction and very much for having me in the first place. Really nice of the organizers for me asking doing this keynote, and I'm happy to do that because this is a topic. The topic I'm going to talk about is a topic I am sort of very emotionally attached for many years. So I work and we work in the domain of quantum computing now for almost 10 to 15 years. I did my PhD in this topic, and apparently, particularly in the past few years, this topic become more and more important. You know, quantum computing got momentum right now, and although quantum computing was mainly covered by physicists in the past, now issues for engineering and issues particularly for computer science and for software science becoming more and more important. And in this talk here, I would like to give you a rough overview on the kind of methods we developed. Eventually, those are methods which we built into software tools, but the underlying ideas and concept, they heavily rest on what we call design automation. And what I mean with that and what kind of sort of challenges we're addressing with utilizing concepts of design automation for software tools, this is sort of what I wanted to discuss and what I want to present in the next, as you said, 45-50 minutes. And before I start doing that, let me quickly provide a little bit context and motivate a little bit our work. And this is a workshop on quantum computing, so I guess most of you will be familiar. So I won't give a very in-depth introduction to quantum computing, as we probably all know here in the audience, that quantum computing is certainly one of the next big things. There are lots of emerging technologies and important technologies which are on the horizon right now. And I'm not saying that quantum computing is the only next big thing, but it is certainly one of those things which will become much more and more relevant in the next years. And we can see that because many players are heavily investing in that. Of course, technology players, IBM, Google, Microsoft, Amazon, the who's who, but we also have got lots of new startups like Rigetti, IonQ, AQT, and so on and so forth. And also more and more big players also from the application domain, like Volkswagen, who sort of invest a lot of money in order to investigate whether or not their logistic or optimization problems can be handled. BMW, Infinity, lots of players play around. And you can also see a sort of, and of course, this is all motivated by the promises of quantum computing. It can provide exponential improvement in the best case. And we have already a lot of applications which show these promises. So one killer application is, for example, improving this Haber-Bosch process. This is a chemical application. There's also some sort of a subdomain, quantum chemistry, who's working on that. And using quantum computing, you can substantially improve the chemical processes here. Of course, most of you most likely have heard about integer factoring. Here, quantum computing may provide a promise, because it may be possible to solve integer factoring in polynomial time, while all the existing solutions so far always have exponential time. And of course, because of the because factoring is so important, particularly for cryptography, this could be a complete game changer. And there are lots of other applications in machine learning, physics simulation, unstructured search, optimization. And what is important to know at this point, of course, all those are the currently investigated applications. And some of them, like this Haber-Bosch process or particular optimizations problems, are more on the new term perspective, and others, particularly integer factoring, although already discussed for quite a while, this might be an application which is still more on the long-term perspective. But motivated by all these kind of applications, sort of the interest in quantum computing got enormous momentum. And this is not only because we already have these kind of applications which sound to be promising, but also the quantum hardware evolves substantially. There's a substantial process in the recent years. I was mentioning before that quantum computing was mainly considered by physicists so far. And indeed, those physicists made impressive improvements in the recent years. So we've got first machines, and also the scalability of this machine improved. And just as an example, the IBM roadmap, for example, looks at the moment something like that. So they started in 2017 with their first publicly available quantum computer, and now they increased the machine substantially. We'll have a couple of hundreds of qubits working today. By 2023, they are planning for more than 1,000 qubits. And what I found particularly interesting, they didn't attach the precise year to it, but IBM is currently really speaking of that in the future, they're going to have millions of qubits. And even if you consider other metrics, not just the number of qubits, but also a metric like the quantum volume, for example, which is kind of sort of a measurement to sort of a metric for the power and the computational power of a quantum computer, then you can also see the increase of this metric with different machines. So those are different IBM machines, and you can see the increase of this quantum volume, of this computational power, is also increasing exponentially. Of course, those are just very few data points, but it kind of looks like that we are currently seeing a development which actually is very similar to the development of conventional machines. And when we go back, I don't know, 70, 80 years ago, then we had a very similar picture with conventional computers. So we first had computers which were occupying entire rooms. And in the meantime, we probably have heard about Moore's law. With the technological improvements, we eventually ended up with exponential improvement in the computation power, in miniaturization, and literally this led to something like that. Computers which originally consumed entire rooms, now we have that in our smartphones, we have that in our cars, we have that everywhere. So computers, conventional computers, made a tremendous improvement and development. And we see that kind of in quantum computing as well. Quantum computers so far are still kind of bulky, but as I said before, you can see this improvement, and it looks very much that we now have a similar improvement and similar development in the physicalization of quantum computers as we have seen it in the past decades in the conventional computers. And what sort of does this bring to the table is the following, that if in the conventional world, we've seen all those improvements by the electrical engineers and this method, and then at some point we recognized, okay, it is not just sufficient to have electrical engineers working with these kind of computers, but at some point we needed programming languages, we needed abstractions, we needed compilers and stuff like that. And I come from the hardware design world, and also here we needed design automation in order to handle this success, because although it is interesting and nice if you can realize a computer with billions of transistors, you as a human being cannot create a netlist anymore, in which you manually position and put together billions of transistors. You need software tools, you need design automation tools for that. In the same fashion as you need compilers in order to translate higher level languages down to lower level languages. So although of course the successes in the physicalization of conventional computers is some sort of a basis, it needed design tools, software tools to handle that. And in the meantime, we had lots of these problems, lots of these solutions available. So tools today use reasoning engines. We have several strategies. We have data structures like decision diagrams, strategies like divide and conquer, A star. And what I'm trying to say here is a little bit, in the conventional realm, we had these computers and they got bigger and bigger, more powerful and more powerful. And we at some point needed design automation and software tools to actually properly use that. And now, considering the development of quantum computing, I would say we have exactly the same development as well. Quantum computers are becoming more and more powerful, but also more and more complex. And because of that, we also have to think about what kind of design automation methods and software tools do we have in order to properly design and use these kind of quantum computers. And here we have to say that when you consider design automation or software tools for quantum computing, then of course we have some tools. You probably know we have Qiskit by IBM, we've got Circuit by Google. So we have tools there. But if I want to compare those tools which are available for quantum computing so far with the tools which are available for the conventional design, for the design of conventional circuits, then I have to say that, okay, we don't have that powerful tools yet. And we also don't have these powerful design and compilation flows yet, right? So if I design the next smartphone or the next AI solution, we have very sophisticated design flows in covering every aspect of the design flow, from the initial specification towards the initial implementation, the synthesis, the compilation, testing, verification. We have fabricated tests, stuff like that. We have very elaborated design flows, but when you check out the design flow for a quantum computing application, I'm not saying there's nothing, but there's definitely not such a sophisticated flow available as we take for granted in a conventional realm. We have some flows, again, IBM, Google, all those players, they build up tools and flows, but nothing as sophisticated as we see in the conventional realm. And this indeed yields the situation where we may end up in a situation where we have a quantum computer or very powerful quantum computers, but no methods to efficiently design or use them. And this is indeed, we in our domain often say that that's a sort of a design gap. We have seen that in the conventional realm for decades. We have a so-called design gap. That means the ability to fabricate a new computing device, for example, was always higher than our ability to actually design that in a useful manner. And this is something which we're now, in my opinion, approaching with quantum computers as well. That means we have to really think about, okay, how can we improve that? And this is sort of the main motivation of our work and also of this talk here, that I want to make the point that we have to get serious in the development of design automation tools, software tools for quantum computing. And with software tools, there are these tools like Qiskit, and so they are already a really, really good step, but we have to get more serious in order to tackle the challenges which are up to. And for this, there are a couple of challenges to be addressed, because if we want to do really sophisticated software for quantum computing, we have to do more than just adapting our conventional software and then just applying it to a new use case, because lots of things changes and lots of things are different. And it's a little bit hard to actually illustrate that very nicely. What are actually the main differences of a quantum computation compared to a conventional computation, but I would like to provide a couple of examples. The most important thing is the entire way of how we program things differs substantially, right? And there are lots of things, and I want to pinpoint to one particular thing, which is not 100% quantum, but is a kind of inherent kind of requirement, namely that every quantum operation is inherently reversible. What does it mean? If I have a multiplication like that, well, that's a very straightforward computation. If you have, for example, two numbers, 4 and 5, you of course can multiply them, and then you get your product, which is 20. And in a conventional realm, that's no problem. You can do that, and everything is kind of intuitive. In quantum computing, an operation like that is not allowed, because everything in quantum computing has to be reversible. And it means, okay, I'm not only supposed to get the output assignment for a given input assignment, but also the other way around. And this is not possible here, because if I have the output 20 and I want to determine the reverse of the multiplication here, I may end up with 4 and 5 again, but I also may end up with 2 and 10. So this is not a reversible operation. And by that, simple multiplication such as that is not possible in quantum computing. And you can find workarounds on that. You can sort of try to embed your actual functionality into something reversible. So for example, by doing something like that, by combining it with a particular so-called reversible assignment operation, not a pure assignment. So you cannot simply say C is equals A times B, but you can say C is increased by the value of A and B. And then if you assume your C is initially initialized with 0, then indeed you can conduct operations in both directions. So this is just one example. It is not impossible, but you have to, have to do these workarounds. You have to think differently. You have to think reversibly. And by that, suddenly, if you want to purely develop something purely quantum computing, suddenly languages like Java and C++ are not sufficient anymore. Which does not mean we cannot use these languages for some applications, but at least when it comes to the pure quantum operations for the quantum part of an application, suddenly these kind of things cannot be used anymore. And this is just the very beginning, because obviously, and this is usually what most of the talks begin when we talk about quantum computing. Obviously, we have this thing that in quantum computing, you're not only dealing with 0 and 1, but you're dealing with 0 and 1 or 0 and 1 at the same time, right? So, and this is, of course, one of these main features and what makes quantum computing so powerful. But at the end of the day, you have to also handle that. You have to handle that. What is the meaning of certain quantum operations? Every quantum operation is a unitary, and does your programmer, does your developer know what a unitary is? We all learned in school addition, subtractions, multiplication, and that kind of stuff. And then when we program in Java and Python, in C++, we kind of used to this conventional paradigm, which we learned in school, but not that many people have an inherent understanding about what is a unitary and what is a unitary operation, or what is a superposition in a sense like zeros and one at the same time. And then not to mention things like there are lots of different physical constraints which have to be considered. We have to make sure quantum computing so far is very prone to errors. So we have to think a lot about error correcting, stuff like that. So lots of things suddenly came up and pop up in quantum computing, which are no issue so far in the conventional one. And software tools, design automation methods, and design flows have to be have to consider that, right? And this requires a huge paradigm shift. And then on top of that, that is not only that we have to talk about these kind of different paradigms, but on top of that, many of the problems in the quantum computing realm, in the design of an application, are substantially harder. And a simulation is, in my opinion, a very nice example to illustrate that. For example, if I have a conventional circuit and I want to simulate that, what I can do is I can simply say, okay, look, I initialize my primary input and then I simulate simply every gate. So this is a NOT gate. So simulating 0 with a NOT gate ends up with a 1 here. And then we can do this here as well. And then we can say this is an AND gate with an 1 as input and another 1 as an input, yielding the output 1 as well. And by doing that, you now can sort of simulate your circuit. And this is actually, this logical simulation here is a linear process, linear with respect to the number of gates. And this, in this regard, it is a rather efficient process. Now, in quantum computing, I mean, this is not a quantum circuit, but just to illustrate a little bit, in quantum computing, simulation suddenly turns out much, much harder, because you not necessarily just have some sort of a discrete sort of input assignment, but you can have an input assignment which can be 0 and 1 at the same time. That means if you have in quantum circuit with 2 inputs, you have to somehow represent the possibilities and the probabilities of all possible combinations. That means of 0, 0, 0, 1, 1, 0, and 1, 1. And this is usually done in terms of a state vector. That means an input state in a quantum circuit is not anymore just a fixed vector 0, 1 or a fixed assignment 0, 1, but it is actually so-called representation in terms of so-called amplitudes for all possible assignments, and you have to explicitly store all those kind of amplitudes. And in this case, for a quantum 2-qubit system, you need 4 of those amplitudes. And for a 3-qubit system, you need 8, and for 4-qubit systems, you need 16. It means, the long story short, you have an exponential complexity if you want to simulate a quantum circuit. And this, in my opinion, is a nice example because it shows that suddenly a task which is simple in the conventional realm, namely simulation, a logic simulation, suddenly turns out to be exponentially hard in the quantum realm. And this is another example of what kind of challenges we have to tackle. So what we have to be aware and why development of software tools and design automation tools for quantum computing is so important is that on the one hand side, we have to familiarize ourselves and the developers and the programmers with this different paradigm. And then at the same time, we have to tackle suddenly much more complex problems. And the development of software tools has to sort of consider that. So the main motivation of our work is how can we develop software tools which kind of address these kind of challenges, so that we, as we are used to it in the conventional one, that we can use software tools and design flows to ideally automatically and efficiently realize our application. And this is sort of what these kind of tools need to provide. And right, and then on top of that, further challenges is, of course, if you work in quantum computing, you have to work interdisciplinarily. So at some point, you need to understand what the physics, what the physics physicists talk about. You have to understand physical constraints. A huge problem in the domain until today is we have different kind of terminologies, different formalizations. This typical problems when you work in interdisciplinary fields, you talk to a possible partner, which might be a physicist, and then you need 4, 5, 6 meetings until you figure it out that the right language, and until you recognize that you all the time talk to each other, but didn't really sort of talk, didn't really got, so that it is a huge effort to actually get sort of some progress in interdisciplinary work. And what I want to do in this talk here right now is, so with this motivation, I want to give you some snippets, some examples of some of the contributions we have done in the past, how we can provide solutions for the challenges I just mentioned, because this is sort of like our main focus here, that we developed automatic methods and tools which addresses these challenges and which helps to design quantum algorithms, quantum circuits, and quantum systems in general. And for this purpose, I want to cover 3 particular aspects, which in my opinion are really important in order to tackle that. In order to have efficient software, it is not just sufficient, in my opinion, to just hack some software down, but you really have to think about, okay, what kind of core methods do you want to use? What kind of data structure do you want to use? In particular, if you know, as I said before, the representation of a quantum state is already exponential, I might want to think about how to represent this exponentially large entity efficiently in terms of software. So I think before we even start solving any problems, thinking about what kind of data structures, what kind of methods should be used for that is key in order to eventually develop efficient methods. And then I would like to illustrate a little bit how does a compilation flow look like so far, and what are the challenges here, and how can we improve upon the current state of the art. So then that's what I want to cover second. And last but not least, I also want to talk about, I already motivated simulation a little bit, but also verification, or checking that your application actually works as intended. This is then the last example I want to illustrate. And for all those 3 aspects, I want to give you just sort of an intuition, some sort of an illustration, and sort of main idea. And then I have links to corresponding GitHub repositories where you can find corresponding implementations and more details, so that if you're interested in some of those directions, you can sort of try out the software on your own, or dive a little bit more deeper into the documentation or the corresponding paper. So the idea is, in this talk, I'm trying to give you a glimpse in what you can do. And if you really find that interesting, then I also have a couple of material for follow-up, for more in-depth follow-up investigation. So starting with core methods and data structure. I already mentioned before, a big problem is that you have suddenly many entities in quantum computing are exponential in size. I already mentioned the state vector in the beginning, but the same also holds for operations. So any single quantum operation can be described in terms of a matrix, a unitary matrix as shown here. So this matrix represents some kind of quantum operation. And those matrices, they grow exponentially with respect to number of qubits as well. That means if you have a 1 qubit operation, you can represent that in terms of a 2 times 2 matrix. If you have a 2 qubit operation, you need a 4 times 4 matrix. With 3 qubits, you need 8 times 8. It grows exponentially as well. And now the idea is, okay, what kind of data structures can we come up with which may help to represent that in a little bit more compact fashion? And one data structure we particularly investigated are so-called decision diagrams. What is the idea here? The idea is first to decompose our matrix into submatrices. A submatrix 1, a submatrix 2, a submatrix 3, and a submatrix 4, and then to represent those matrices in a fashion like that. So that you have this submatrix here is now represented by this successor, and this submatrix is represented by that successor. So you have literally one node here with 4 successors, and each of those 4 successors represents the corresponding submatrix. Having that, we didn't save any kind of space right now. We still have an exponential number of entries. But what you can now do is you can now try to exploit redundancies. As an example, you can see these 2 matrices here, they are equivalent. So there's no need to explicitly store them. I can simply merge them. And then I already save 25% of my memory requirements in this particular case. It's one thing you can do. Another thing is you can see all those entries here, they sort of are values which all have the same factor, namely 1 by 2. So you can multiply that out, and then you end up with something like you put the factor, the common factor, on the edge of this, as an edge weight on this edge here. And then this is now the matrix. And what you now do is when you take this edge here, you encounter this edge weight, and then you know, okay, you have to multiply everything what you see here, you have to multiply it with 1/2, then you get this representation. How does this help? Well, if I do the same thing here, for example, by multiplying out -1, originally this was my original submatrix, now I multiply out -1, then I get this one here. And then I again end up in a situation where these 2 submatrices are identical, so I can merge them. And now I have 2 successors pointing to the same node, one successor just assuming factor 1, and another successor assuming factor -1. This allows me to also share these kind of amplitudes, so I save memory again, even though those matrices originally aren't completely equal, but they are equal with respect equal except for a common subfactor, which I simply put into the edge weights. And by that, suddenly what I accomplished, I have something which had, I reduced the overall memory requirement for that by 50%. So I saved 50% of the amplitudes. And now I can recursively do that as well. I can now decompose this matrix into submatrices and this matrix into submatrices. And then by doing that recursively, I can merge again. And then by doing that, I end up eventually in the representation like that, which I can then represent in terms of a decision diagram as that. And in the worst case, if I don't find these kind of redundancies I talked about, then I don't gain anything. But in good cases, or even in the best cases, there might be certain functionalities which allow me to represent this exponentially large matrix in polynomial space, or sometimes even in a linear space. So depending on the unitary, I may be able to much more efficiently represent this operation in terms of this decision diagram. And this is an example of why data structures are important. The straightforward realization of a unitary matrix like that would be a 2-dimensional array in any programming languages you like. But the more sophisticated solution might be these decision diagrams. And then this could provide the basis for a very efficient software tool. For example, we talked about the simulation before. And now I would like to sketch a little bit how you can utilize this data structure, these decision diagrams I just introduced, in order to improve simulation. Simulation, as said conceptually, is actually very simple, because if you have a given quantum input, a quantum state, like an input state, like this one here, and you want to simulate a particular quantum operation, the quantum operation usually represented in terms of a matrix, all you have to do is you have to simply multiply the matrix with the vector, and then you get your output vector. So conceptually, simulation of a quantum operation or of a quantum algorithm or a quantum circuit, conceptually it's easy, it's just matrix vector multiplication. The challenge, as said, however, comes from the fact that the vectors and the matrices are exponential. So let's give an example. We have an input state 1 represented by this matrix, an operation H represented by that matrix. If you want to know what is the output state of, if you apply 1 to the operation H, you multiply this matrix with this vector, and then you end up with this, which is literally this state here. So the actual way of doing simulation is simple, and now we just need a way to get around with the to handle this exponential complexity of the matrices and the vectors. And here, these decision diagrams I mentioned before help a lot, because what you now can do is you can now represent those operations and states by means of a decision diagram rather than a two-dimensional exponentially large matrix. And then you can use these decision diagrams, this data structure, to improve the simulation. And we've got some results on that, which show actually what is the potential of that. And for this purpose, for example, we considered Microsoft's Liquid simulator using, and we simulated Shor's algorithm. This is this factorization algorithm. And using this simulator, which heavily relies on parallelization, but on more or less two-dimensional arrays, we required 50 gigabytes of main memory and 30 days of simulation time. While in comparison, when we used the proposed decision diagrams, we suddenly were able to simulate the same instance with just 100 megabyte and in less than 1 minute. And this shows a little bit the potential we have here. And a very important disclaimer here, this does not mean that these decision diagrams always allow these kind of very sort of impressive and drastic improvements, but it shows that it can accomplish that. To be really transparent here, we also have many cases where the data structures, as I proposed, as I presented here, actually require more runtime and more memory. There are a couple of reasons behind that. So I'm not saying that this is the silver bullet which solves all the problem. It just showcases a little bit that for some applications, like Shor's algorithm here, and for simulating that, there might be indeed the case where where it might be very beneficial to use dedicated data structure. And we have lots of further solutions as well. So for other cases where with this data structure, you can actually get lots of improvement. So the bottom line here is, if you have a good data structure, you might be able to get tremendous improvements. And as said, if you want to try that out, it's a software workshop. So I thought maybe it might be nice also to pinpoint you a little bit to software. A simulator based on this decision diagram has been implemented in terms of a so-called DD-Sim simulator. It is available on this GitHub, and once you clone the GitHub, what you simply can do is, I'm not going into much detail, but just with a small Python script like that, you can instantiate a quantum circuit. You can then instantiate the corresponding simulator. You run the simulator, and then you sort of execute the job, the simulator, you get your result, and then you can see, okay, for this quantum circuit, with the particular input you get, you simulated that 100,000 times, and then you see in 50,149 cases you got 000 as output, and in the remaining cases you get 111 as output. So you can really play around with that with just a short Python script like that. And this is an example for how data structures can help, and how data structures in this case can help for simulation. The second topic I wanted to briefly provide you an intuition with is compilation. And this is very similar to the conventional realm. Again, you have a high-level description of your application, and you want to compile it down to a low-level description. And you can do that using compilers. And we have that in quantum computing as well. You have originally something like a conceptual algorithm, a sequence of quantum operation you want to realize. And you have a machine on which you want to execute that. And in this case, the machine would be an IBM machine, an IBM device composed of 5 physical qubits. And then compilation means, okay, you have to sort of translate this description into a description which can be executed on this machine. And the first problem here is that you might have a limited gate set. So maybe this machine here does not support this particular kind of gate, which is a Toffoli gate. So this is just not a native or not an elementary gate. So we have to compile that down into a sequence of elementary gate, which is the first compilation step. And then, of course, here lots of problems pop up like, okay, how to do this in the most efficient fashion, and can you optimize it afterwards? So this is a big problem. We call that synthesis or decomposition, compilation sometimes. So how to map and how to translate every non-native gate into a series of native gates. Next problem is that usually those machines don't have arbitrary connectivity. You can nicely see that here on this so-called coupling graph. What is not allowed is you cannot, the qubit Q0 here, the physical qubit Q0 here, is not allowed to interact with the physical qubit Q4. Q0 can interact with Q1, but not with Q2, not with Q3, not with Q4. So this graph describes what kind of interactions is possible. And now you as a designer or as a compiler, you have now to decide, okay, how do you map your logical qubits to those physical qubits here? And then you may come up maybe with a solution like, okay, I want to use these 3 physical qubits here, and I want to use this mapping. That means I map logical qubit 1 to physical qubit 2, logical qubit 2 to physical qubit 1, and logical qubit 0 to physical qubit 0. Might be possible. And then you check out, okay, can you execute all your gates? Apparently this execution is possible because here physical Q2 and physical Q1 interact. This is allowed. But then you end up with this gate here, a gate arguing over logical Q1 and logical Q0. Q1 is mapped to physical Q2 and Q0 is mapped to physical Q0. So actually Q0 and Q2 have to interact, which is not allowed, right? And now you can think of, okay, maybe you change the mapping, but then you would destroy those interactions maybe. A solution you can come up with is you add so-called swap gates. That means you move the position of one qubit to another position. For example, in this case, you move the position from physical Q0 to physical Q1. Means you move your logical qubit from here to there. Then your qubit is now neighboring your Q2, and now you can execute this operation, and then you can simply add the gate there, and then you can do that. So by adding additional gates like these swap gates, you can actually satisfy your connectivity constraints. And now the challenge is, how do you do that? So how do you come up with an initial mapping and with an insertion scheme for those swap gates so that you satisfy those connectivity constraints and at the same time keep the number of swap gates you insert as small as possible, right? So this is a typical compilation task as well. And then, of course, we have the problem that we want to reduce the cost because every gate in here is sort of affecting the fidelity of the circuits. It may introduce more errors. That means the more operations, the more gates I have, the more errors I have. So I want to optimize my circuit. And then maybe we can think about things like, okay, I have here 2 H gates in a row, and I now know 2 H gates in a row, they cancel each other out. So I can optimize that. Or I see a structure like that, and then I know a structure like that can be optimized to a more compact structure. And then I may end up with a circuit like that, which is now optimized, and this could be the result of a compilation flow. And what you can see here, and this is the main message I want to convey, you have certain problems. Apparently, all of these problems are very quantum computing specific. So it's not like we are compiling Java code or C++ code in here. But on the other side, and I hope I was able to convey that a little bit, you see problems which sound very similar to what I would call typical design automation problem, or maybe in the software realm, you would say typical compilation problems, because we've got sort of like this mapping here. This is very similar to graph coloring or to scheduling, right? And this optimization here, like this is very similar to term rewriting, which you see in conventional compilers as well. So my main message here is we should reuse this existing knowledge about how we compile and synthesize and optimize conventional realm. I mean, it has been proven that some of those problems here are NP-hard, and we have NP-hard problems in the conventional realm as well. And in the past decades, in the hardware community, in the software community, decades and thousands of engineers and researchers implemented efficient tools and developed efficient methods to handle this complexity. And the situation in quantum computing right now is we're at the beginning, and we have many tools which are built from scratch. And my message is we should more and more reuse knowledge and expertise from the conventional realm in quantum computing, because the problems might be slightly different, but the solutions could certainly utilize decades of research and engineering from the conventional realm. And this is my second message here. And so far, we should work much more on utilizing this expertise. And this is sort of one of the main motivations of our work as well, that we try to develop tools which are targeted for quantum computing, which address these kind of problems, but which do not reinvent the wheel, but try as much as possible of reusing something from the conventional realm. And also here, I said, I'm just showing that also here, tools are available. There's the GitHub, if you're interested in that. And again, with a small Python script, you will be able to compile a given quantum circuit into a realization which is executable on a machine. In this case, for example, on this quantum architecture here. Also here, implementations are available. And last but not least, the final topic I want to use in order to sketch a little bit the challenges and the solutions software tools can provide is verification. And in this case, verification, I mean here particularly the question like, can we prove somehow that our originally given quantum circuit, that our resulting compiled quantum circuit still realizes the same functionality as the originally given quantum circuit. And this is literally the questions. I have two quantum circuits, and I want to know quantum algorithms, and I want to know whether or not they are equivalent. And also here, as in simulation, this is very straightforward to prove, because all you have to do is you have to take all those operations here, which are represented by unitary matrices, and you have to multiply them together. You do this, and then you get a matrix which describes the overall functionality of this circuit. And then you do the same here as well. You take all those gates, you multiply them together, and then you get a unitary representation of this circuit. And then you simply have to compare whether or not both are equivalent. So conceptually, verification is easy. But again, in the real life, it is complex again, because obviously every matrix is exponential in size again. That means for every gate, you have an exponentially large matrix, and then you have to multiply exponentially large matrices together. Obviously, this is where the bottleneck is. You have this complexity problem again. And now I can come back to the beginning of my talk, and I can say, okay, but we have these efficient data structures I mentioned before. And indeed, you can use these decision diagrams for that as well. You can create a decision diagram representing this matrix here, and you can create a decision diagram representing that matrix here. And then if both decision diagrams, that's a nice feature, if you construct these decision diagrams in the same fashion, those descriptions are canonical. That means you can simply compare if both decision diagrams are equivalent. And if they are, you have a proof that both quantum circuits are functionally equivalent as well. And this is the huge benefit here. And this kind of can provide a solution. That means due to this efficient data structure, you may have an efficient solution for verification. But here also, it does not mean, I mean, as I said before, these decision diagrams, they often provide a more compact representation, but in the worst case, they are exponential as well. So also those decision diagrams will reach their limits. If these decision diagrams would be, I don't know, really efficient, let's say if they would be polynomial, in all possible cases, we wouldn't need quantum computers anymore, right? Because we could simply represent everything in decision diagrams and that would be it. So obviously also these decision diagrams have their limits. So also here you may run into some limits. But then, and this is the final thing I want to illustrate here as an idea, then you can still utilize further characteristics of quantum computing to improve the problem. And this is something I would like to show you, because this is something where we maybe can actually exploit quantum computing for our benefits as well. Or to put it another way, so far, most of my talk was about, like, in quantum computing, everything is more complex. Everything is it's harder than in the conventional realm. Well, verification might be a task where it may be even a little bit easier than in the conventional realm, because for verification we can exploit a very interesting characteristic, namely what I mentioned before, that every quantum operation inherently is reversible. And we can utilize that and exploit that in a very nice fashion, because what you could do is, if you have two circuits and if you want to know whether or not they are equivalent, what you could do is you could inverse one of those circuits. And if you do that, if you take the inverse of one circuit and combine it with the other circuit, the resulting overall circuit should realize the identity. So to illustrate an example, if I have two circuits and I want to know whether or not they are functional equivalent, what I can do is I can inverse one of those circuits, which is easy because, as I said, every quantum circuit, every quantum operation is reversible. So I inverse one of those circuits, then I multiply them together, and then I have to check out whether or not the resulting matrix is the identity matrix. And the sweet thing here with the identity matrix is that a decision diagram of the identity matrix is linear in the number of qubits. So it is definitely a very efficient representation. And this is now interesting, because what does it mean? It means if I want to check the equivalence of these two circuits, I just multiply one circuit with the inverse of the others. I have to multiply all those gates together. And if I end up with the identity, I have proven that both are functionally equivalent. However, now comes sort of the small showstopper. If I multiply all those gates together, I still have to deal, in the worst case, with an exponentially large matrix, right? Because if I multiply all those first gates here together, I end up with the original, with the entire, not with the identity, but with the entire unitary matrix again, which might not be efficient. And not before multiplying those gates together, I end up with this very compact decision diagram. However, what you can do here is you can do that in phases. So what you can do is you can start with the identity, which can be represented in a compact fashion using decision diagrams. And then you not multiply all of those gates at once, but you maybe multiply one of those gates from this circuit, and then the inverse of the other gate from this circuit. And then, let me go back again. So you multiply first this gate here, which slightly increases your decision diagram. And then you multiply the corresponding gate from the other circuit, and then you end up with your identity again. And then you could multiply a gate from here and multiply another gate from here, ending up with the identity. And now, of course, this is a rather naive approach so far, but if you have a clever oracle, for example, if you now multiply this gate here, and if you now know that in your compiled version, this gate or this part of the circuit is composed not of the single gate, but of all those all those gates here, then you can cleverly get back to the identity again. This requires some sort of an oracle or a good heuristic. But the main message is a little bit, in principle, conceptually, you can have two arbitrary circuits, and then you can multiply a gate here, and then multiply the inverse of a gate from the other circuit. And if you do that in a clever fashion, you may be able to sort of multiply all those gates together, while at the same time staying at this very compact identity matrix, or close to identity matrix. And by this, you can actually verify the correctness of the equivalence of these two circuits by and while at the same time staying often close to the linearly large decision diagram. This, of course, only works if you sort of, if you know a little bit that, okay, this gate belongs to that gate, and that you know that you had applied some swap gates here, and that you know that you applied some optimizations. So, of course, if you know all this information from the compilation flow, then the problem is rather simple. And then maybe you don't need a verification in the first place, because you could easily verify these steps on your own. But even often compilation flows and complex design flows, you don't have all this kind of information. You have an initial high-level description at the very beginning, and then dozens of tools with different configurations, dozens of design teams changed the representation, and then you end up with a compiled version where you don't necessarily know all these kind of details anymore. But if you still have some sort of a rough oracle, which roughly estimates how these two circuits stand to each other, then you may be able to verify the equivalence of these two circuits, and by this, the result of a weeks-long design process in linear efforts. And this is something conventional verification cannot provide. And I'm not saying that in quantum computing, this is a free lunch. It is still an open research question, but the potential certainly is there. And research would be needed in order to check out how much we can exploit this potential. And also here, just for the sake of completeness, also here an implementation is available, and you can use and play around with all that. And just very briefly, coming to the end, also here, this is, I don't want to dive too much deeper into it, but we also here have further methods, particularly for verification. Stat solving is very has been established as one of the core methods. In the conventional one, we use stat solvers a lot. There is research going on how to utilize stat solvers also in the quantum realm. But as said, overall, with these three examples, with the importance of efficient core methods and data structures, with the importance of compilation and synthesis, and with this sketch on verification, I wanted to illustrate a little bit how software tools and how design automation methods can help here. And well, let's wrap that up. To the end of my talk, so to summarize my talk a little bit, what I try to convey here as the main message is, if you have efficient representations and data structures, then you can tackle problems like simulation in a very efficient method. And for this, tools are available. We have tools for compilation, we have tools for verification, which utilize these kind of things. And all those tools are available in a GitHub so far. And if you don't want to install any tools, we also have as a web-based tool where you simply can go in. So for example, if I can quickly switch here, we have a tool, for example, here, where you can click on the simulation tab, and then here you have a couple of quantum algorithms, and this is some Quasar code. You can, if you like, you can edit the code here, and then you can simulate that, for example, by just hitting on this button here, and then you have simulated the first X gate here. Oops. And then you simulated the H gate, and so you can literally simulate now your code. And at the same time, here you can see how the corresponding decision diagram looks like, and here you can see the information about the state vector. So also for that, tools are available. And again, the main difference here is those tools are not just tools like Qiskit, which helps you to realize circuits and applications, but those tools have to focus on how can we explicitly utilize design automation expertise, how we can utilize the expertise from decades of research in engineering and software science and hardware science. So they try to really exploit that for the domain of quantum computing. And almost last point here, even if you didn't got the main idea about these decision diagrams, or didn't got the main idea about the verification approach I was sketching, all of these tools can be used as a black box. So you can still benefit from these tools, even if you didn't understand how they work in the internals. If you haven't got the idea of the decision diagram, doesn't matter. With the Python scripts I showed you before, you can still use the tools, even if you don't know, even if you don't want to know how they work internally. So also this is a good thing, and we are kind of successful with that, because in the past years, our tools got integrated into Qiskit, into IBM's Qiskit, into Athos's QLM, because we're really developing these tools also with that in mind, that people want to use that, or researchers, developers want to use that without understanding the details. And with this, I'm completing my talk. Thanks again. I would like to thank again the organizers for having me, and of course you, the attendees, for your attention. And if you want more information, here is our webpage, and where more information is available. And of course, also on our GitHubs, we provide information. I hope I was able to convey a little bit message why it's so important that we get serious about tools for quantum computing, not just in a fashion as it's done with Qiskit and Cirque and Forest and so on and so forth, but also when it comes to the internals, to the data structures, to the methods we develop in order to tackle these tremendously hard problems. With this, thanks a lot for your attention. And of course, if we have time for questions, and if there are any questions, I'm happy to address them. Thanks a lot.
Thank you very much, Robert. That was very impressive pieces of work that you presented. And yeah, so we have now time for, we have about 8 minutes for questions. So if anyone has question and would like to answer, would like to ask, they can ask directly, or they can also post their question in the chat. So yes, any questions from the audience?
So since I've raised my hand, thanks a lot for this very interesting talk. And well, the $1 million question, which I'm sure you've already considered, but I'd like to know your position on that, is how do you handle noise? Because with noise, the nice unitariness becomes suddenly non-unitary, and then I would imagine that the decomposition into identity breaks down. So how do you handle that?
We start considering diving into this as well. We didn't consider it for the verification so far, but for simulation for sure. And here there are different methods how to handle that. There exists already. That's the reason what I mentioned. We have to closely work with physicists on that, and there exists models for noise. So we have noise models, error models. And you're absolutely right. This makes a problem that when you consider simulation, I already was saying simulation is exponentially hard because of the exponentially large matrices and vectors. And if you now additionally consider noise, we make an already hard problem even harder. And there are two approaches which we considered so far. One is an exact approach. We represent all the possibilities and all the probabilities of errors and error effects in terms of so-called density matrices, so-called Krauss matrices. So you can, and then you don't have an 2 to the power of n times 2 to the power of n matrix anymore in order to represent an operation, but you have an 2 to the power of 2 to the power of n matrix. So you simply increased exponentially one magnitude further. And with this, you can simulate quantum algorithms, including errors in a very exact fashion, but you're absolutely right. Then we suddenly are much more limited than we already are right now. So we can, at the moment, we can just simulate very, very tiny applications for that. The alternative is doing a little bit more on a stochastic approach. So we take the original simulator and then we just run it a lot of times. So we do a lot of samples, and then based on the probabilities, we inject errors depending on the respective probabilities. Then you don't get an exact result anymore, but you might be more efficient. You can also parallelize that better, and then you get a result like that. This is the two approaches we considered so far.
Okay, cool. May I ask what error models or what noise models you are considering in the density operator picture? Is that Zoller Gardiner or something that goes beyond that?
Much more simpler, probably. Decoherence errors is the typical one. So, like if you have the qubit state 1, that over time it decays towards 0. So this is sort of the model. It's called T1 model, and the other is a T2 model. I don't have, to be frank, I don't have the definition completely in my mind right now. But those are the, to be honest, we're at the very beginning here. Those are the simplest models we are aware of so far. Completely, when you use Lagrangian or something like that, things certainly can get more and more complicated. We just want to get, our foot on some solid, more simpler basis first. And once we sort of figured out how we can tackle that, we maybe dare to trying a little bit more of the complex ones. But so far, decoherence errors are the simplest errors we considered so far.
Yeah, cool. That's very exciting. Thanks a lot.
Yes, so we still have few more minutes for questions. So any questions from the audience?
I would have one if no one else wants to jump in. So yeah, from my side as well, thanks a lot, Robert. It was truly impressive, especially because I am a complete outsider. I'm into software engineering, but never looked into it. So actually, for me, it was a great introduction. It was such a good overview. So I feel like I understand at least a little bit of
Thanks,
what's out
appreciate
there.
it.
And so my question is, when you start explaining, for example, especially the compilation side and all the possibilities on how different the instructions have to be compiled and all the techniques for that, something that keep hitting my head was for how long this will actually be a concern? Because as the amount of qubits, for example, evolve, or any sort of standards may arise on how these the processors are built, I wonder just for how long this is an issue, or if this is something that will always be there, or it's just a momentary problem as the technology evolves.
You mean how long the task of compilation is going to be an issue?
Yes, I think so. Yeah, especially because you mentioned, I think there's some, for example, the different configurations of the target device.
Yeah.
So
Yeah.
for that reason, yeah. So in that regard,
I would say that maybe I shouldn't say always be an issue, but that's going to be an issue for a long while, for a long time. It's very, and on this abstract level, we can perfectly compare that to the conventional realm as well, where we're still having compilers, because obviously not every machine is supporting every native operation. And we're going to have that with each new generation of a quantum device. We're going to have new operations which are supported and new connectivity constraints. So I'm pretty confident that compilation is something which won't go away in the next few years, because we have that in the conventional realm as well. And every compilation is needed in order to realize a high-level application on an actual machine. Right now we have just small machines, and right now the machines will definitely get more powerful. They will get bigger, and with this also the compilation problems will get bigger.
Yeah, so certain types of problems will always be there, no matter how much the machinery evolves. I see. Thanks a lot.
My pleasure.
So we have one question on the chat. I will read it out. So it's from Hangli. So he says that thanks, Robert, for the great talk. Do you think QC is more like the traditional hardware circuit design, programming plus synthesis plus physical placement of transistors, or traditional computer system design, programming plus compiling plus running on general purpose processors? As far as I know, the current quantum computers are general purpose computers, and we do not change the physical location of the qubits in any way, right? Is the optimization to overcome the physical limitation of general quantum computers? In this way, it is also more like optimization in programming, but not optimization, place and routing in IC design.
Okay, cool. Lots of long question. I hope I can probably address that. There is, I'm a little bit reluctant to give a clear yes/no answer here. So probably yes and no is my answer. I'm absolutely confident that a huge portion of the problems we're talking about here are very similar to established problems. Like as I was showing on the slide here, many of those steps here are typical NP hard problems, typical EDA problems. So I really believe, and this is one of my main messages, I want to convey in this talk is, let's not reinvent the wheel. Right now, lots of tools are out there which try to solve compilation problems or simulation problems from scratch. And I honestly believe there are a lot of solutions which we can simply, a lot of conventional solutions which we simply have to adapt for those particular problems. However, there might also be other aspects where we indeed have to start over again, because a conventional approach won't get us somewhere. But overall, I'm a computer scientist by heart, and I keep telling my students that almost all problems of the world, maybe except world peace, particularly in these days, almost all problems in the world except world peace can be boiled down maybe to 10, maybe 12 typical standard computer science problems. And we have decades of research available on reasoning engines, on data structures, and how to tackle these problems. And my first approach always is, I see a new problem popping up, for example, here in quantum computing, in computational quantum computing, and the first thing I think about is not how can I solve that problem from scratch, but what kind of similarities does this problem have with the conventional compilation problem, or with a conventional place and route problem, a conventional scheduling problem, and then I try to boil it down to that and try to reuse as much as possible as we have from conventional scheduling, because in my opinion, this is the best way to approach, because we've got decades of research on conventional place and route, and hundreds of researchers already work on that. So who am I that I start trying to develop a solution from scratch? I first try to get as much as possible out of the existing state of the art, and then see how far we've got with them. And then there might be certain very quantum specific things and issues where we need indeed something from scratch, and then we develop that on top. So it is sort of like, there's, in my opinion, much more potential which we haven't utilized yet. And I would always propose to do this first, and then for what's left, we probably have to, you know, think again and then start from scratch.
Thank you, Robert. I totally agree. Thank you.
All right.